Hi everyone. Uh, Welcome to another episode of the Haskell Study Group. I'm your host Ron Batum with Atlanta Functional Programming, and I just noticed on our live stream that I need to switch buffers here. Okay, we're now on our Haskell Study Group. Today we're going to be discussing algebraic data types, a topic that I'm sure many of you were looking forward to because it is kind of at the heart of how we would design our types inside Haskell. Okay. To understand and write it and knowing how to write your own data types means that one is designing things that could leverage some of Haskell's pretty most powerful features inside of your language, stuff that we've already kind of leveraged: pattern matching, type checking, type inference, the use of type classes for kind of parametric polymorphism. These kinds of things are very useful when you're designing large-scale systems, and Haskell allows you to do this by defining your own data types and then implementing some of these mechanisms so that you can leverage what you need and get that in a statically compiled, statically typed way. The first thing to understand in order for us to kind of really discuss, uh, kind of the features that are available in Haskell is to first understand what we mean. What does Haskell mean when they are talking about uh, algebraic data types? What do we mean when we are saying what is the algebra of an algebraic data type? This is something that's very important because of the fact that as you end up defining your own data types, leveraging this definition will allow you to number one, make sure you don't make certain mistakes when you are doing type design, because types are very fundamental to properties that are associated with programs, and actually Haskell makes a very decent case to saying that if you design your types right and you've aligned them correctly, you can almost use your program as a construction proof as for its correctness, because the type properties are set up and aligned. It won't accomplish everything else, like things that whether or not the types implement a particular user's requirements correctly. That's a completely different discussion ultimately, and it's actually an exercise in software engineering. But certainly, if you want certain properties to be available and want certain types to have these properties available, designing your types appropriately makes it certain that Haskell can then leverage its powerful mechanisms to ensure correctness of the usage of those types. Okay. Now, we've kind of covered types in many ways in a couple of episodes, especially on our discussion of type classes earlier on. This was also reinforced when we discussed the list data type, because the list data type is actually a type of an algebraic data type. Okay, but one thing that is that we did not go through is some of the underlying terminology in detail. Right, we kind of introduced you to the syntax of what an algebraic data type is, but we didn't actually really dive into what those meant. Okay. Now, in terms of what's available in Haskell when you are designing some of these data types, we actually know that Haskell provides, some types. We've actually looked at some types before, product types as well. This is tuples are one form of a product type. We've also talked about type aliases to an extent. But one thing that we didn't actually cover when we were talking about product types is the fact that there are two different syntaxes when it comes to product types, okay? The one that we covered was one related to tuples, and we're talking about pairs as well that falls um, into that umbrella. But there's also, so tuple syntax is one way, but there's also, in addition to that, we also have record syntax. So this would be actually more familiar to those of you who come from, your run-of-the-mill programming language, the modern programming languages, the mainstream programming languages. That's the phrase that I should be using, because record syntax looks a lot like structs. It looks a lot like objects inside other languages. Also, the folks who are coming from the web world, whose primary language may have been JavaScript. Record syntax, the closest analogy there is obviously JavaScript object notation. And we'll cover that, as well. We also, at some point, kind of covered this kind of notion. We're going to be diving a little deeper today about this discussion, time permitting, with this kind of special data type that's available in defining data types, and that's called new type. All right, new type allows you to be able to define data types with a different set of options and constraints that are slightly different. It provides certain things for different that are slightly different than type aliases and data declarations. I'm currently not. Hopefully, we will cover it, but I don't think time permitting that we'll be able to cover that particular piece yet. We may cover it next time. So today we're going to be kind of diving into kind of some definitions and terminological foundations that are necessary, so that when you look at Haskell documentation, and if you actually ever decide that you need to go and read, say, the Haskell report or any corresponding papers that are written for Haskell, you understand some of the terms that are leveraged and what they mean. All right. And we'll cover a couple of those later on through this discussion. But right now, just know that the purpose of today is mainly and the purpose of this chapter, as I understood it, is mainly to cover some necessary foundations that are required to communicate how types are being designed and how Haskell ultimately leverages these types and so forth. We'll also cover kind of what a data constructor really does, okay, and we'll also kind of introduce what a kind is. Okay, a kind is something that's specific to types and type design, right? And based on these, and again, time permitting, because this chapter itself and corresponding chapters that are in Learn New Haskell are quite involved, because the nature of designing and creating custom data types for structuring and describing data that we're dealing with in a larger scale system is a very fundamental piece to the Haskell programming experience, if you consider Haskell kind of like this platform for designing things, not just a programming language, right? So you need to understand how you break down your particular domains or your problems in such a way that you can model them accordingly based on the rules that are available for you and the facilities that are available for you inside Haskell, okay? Although Haskell is a general purpose programming language, it does come with certain rules that to fully leverage its features. So you need to, in many cases, sort of shed any sort of preconceived notions on how one might leverage Haskell with respect to one's experiences with other languages, and kind of learn the Haskell way to define a problem inside its type system, okay? So you can use the type system effectively, right? So this involves obviously two different kinds of things that that I think is important to note, and that is when you're talking about data declarations and type design, you need to talk about one this notion of modeling the domain, right? And these ultimately are going to be your types themselves, okay? And this could be basic types or type classes, even in some cases, okay? And then in designing and type design principles. And the second aspect is obviously thinking about computations that solve a particular problem using your domain model. Right? This is something that is necessarily to bring up just because I think it's important to recognize that at least the way the book kind of covers it, it is the basis for a lot of what sort of types type design strategies you can leverage, okay, to get the best out of what's available inside of Haskell. All right. They talk about some advantages of this in the book, and I think some of it is about proselytization for Haskell, because the claim is it makes your code easier to read and use because the domain model is kind of laid out. I am still kind of learning this language, so I can't really say I agree or disagree with this statement. But for those of you who are more in tune with Haskell, feel free to correct me and give me an example where it clearly defines the types to make them easier to read. Because again, it went back to my previous statement. Type design does not necessarily mean what we've implemented all the requirements associated with a particular problem or application problem that we're trying to solve. And those are, I think, two different discussions that we need to have during the course of designing a live system. To understand how we define a type, you need to first understand our data constructor and type constructor stuff that we've covered in the past, but you need to understand them more detailed again. Recall when we talked about something like, say, type bool, type bool is, not type bool, it's info bool for this particular case. Info bool, we had this data constructor that consists of, false or true, okay? And we know that, and we mentioned before, that this is an example of a data constructor defined as a series of type constructors. A type constructor defined as a series of data constructors, okay? And but we never actually went through some of the kind of like the nuances associated with it, okay? So I'm gonna spit out kind of the one kind of interesting discussion here that we kind of went through in the past in previous discussions, but we're going to go and dig into them a little bit here. So many of you know that in our data constructor definition, we are ultimately defining a data declaration or a data type, and we're using that as a rule of, in this case, for bool, has a series of other data constructors, all right? So when you are defining a data type, and again, this is just going to be a quick review. We all know that we have to use the data keyword to start the definition of a data type. Okay, well, we are signaling to Haskell that we are creating a data declaration or a declaration of a new data type. Okay, that's something to be keep track of, right? We also know that after that, the name that we provide is the representation of a type constructor. Okay, this is important that you know that this is a type constructor, not a data constructor. All right. The data declaration syntax separates the type constructor, which is on the left-hand side, from one or more data constructors, which are on the right-hand side. Okay. And if you recall, that equal sign is basically saying we're defining the type constructor has a series, has one of these different data constructors, and it depends on whether you're doing a sum type or a product type to determine, what type it's dealing with. Okay. Now, in this data constructor, notice we have actually technically two data constructors, right? We have false and true. False and true are, if you recall, nullary constructors because they don't take any arguments. And this is something that's important to understand because what this represents is a data value that can show up at the term level. That is when you assign something to, like, say, a variable. All right. This is different than, say, the case of the list here, which defines a data constructor for a list of some type A. All right. And again, we know that this, just like this is also a sum type. Just like bool, the list is also a sum type. The difference between these two, if you see here, is whereas the bool doesn't require any arguments, all right, the list does. But what is that argument? The argument, okay, to the type constructor on the left-hand side represents the requirement that in order for something to be considered a list of some type, it requires some instance of some concrete type in order for the type to be constructed. Okay, so this is what we call a polymorphic type. Okay, all polymorphic types, if you recall, have type variables, usually represented in lowercase, that tells you that that type needs. Some generic type needs to be available in order for this larger type to be constructed. Okay, you could think about this analogy to generic programming and generics in other programming languages when we're dealing with parametric polymorphic types, because it's very much the same thing, right? Especially when you talk about something like, say, C++ templates, because that in that representation, and again, this is not a one-to-one necessarily. There are some nuances that make them definitely different, but it is a close analogy that I could share with you. In that, if you define a template, we know that what we're defining in C++ is essentially a type factory, generates type definitions based on a concrete type being passed in at instantiation time. There's a thing called template instantiation time where you end up taking the concrete type, and then the compiler will go and generate essentially a version of that type. Okay, and this includes for anything from function templates, which we see some equivalents here in the parametric functions that we've already dealt with thus far, and class templates as well. The difference is that the type system in Haskell actually has a meaning to this polymorphic type variable, and we'll be discussing that in just a moment. Okay, but the takeaway here is in order for any sort of like types that take in a type variable, type constructors that take in a type variable as an argument, it means that it requires a type, a concrete type instance, in order for it to satisfy and construct itself. So it will become a list of something, all right? Otherwise, it can be a list of anything, and that could be potentially problematic later on, okay? So notice when I say list of something, that's something which is one or more things could be of that something. They all have to adhere to that same type contract that is passed into list, okay? This is why you can only have a list of ints or a list of doubles, all right? You can't necessarily have a list of ints and doubles, all right? Or list of ints and structs, because that ultimately is, first off, a tuple type, and number one, but more importantly, it breaks the contract of what a list is. It's a list of items of the same type, okay? When you look at the data constructor of the actual type constructor, notice that the first definition is actually of the empty list, all right? And then the second it takes in ultimately the type variable argument and does a construct by passing A in the list of A to a con cell, representing that we could prepend A to a list of one or more A that's already available, all right? And that's what defines the type, okay? There's a couple of terms here that I wanted to kind of bring up. We've kind of already talked about some types. We've already talked about product types a lot. We've also saw that we have this these type variables that are nullary constructors here, and in a sense, this is one way of defining an enumeration, because what is an enumeration other than a series of constructors that have 0 or more arguments, okay? Now, another definition that you could think of when you're thinking of types is an enumeration that contains 0 or more arguments. So Boolean is a type of enumeration that contains 2 possible data constructors that take 0 arguments, whereas our list type can also be considered an enumeration, where it enumerates 2 possible different constructors, one that takes no arguments and one that takes in 1 argument and constructs them. Or actually, one of them takes 2 arguments, because technically the non-empty list is also an argument passed into that conv operator that's there. Product types we've kind of addressed a little bit with tuples, but we will dig into the discussion of product types a little bit more later. But first, we need to talk about these data and type constructors a little bit more, all right? When we talk about data and type constructors, right, we need to understand at what level we're actually dealing with types. This is something that I had to learn a little bit and try to wrap my head around. I had to remember this a little bit better, but it makes some sense. I'm going to try and explain kind of what the book kind of addressed. I felt that some of it is a little bit more pedantic in the book, but I think I'll try and come up with a kind of a little simpler explanation, at least as I talk about it. All right. So when we talk about type constructors, we're talking about constructors that are normally leveraged in type signatures, type class declarations, and instances of these types. Okay. So what these three are considered are considered the type level considerations for a type. Okay. So when we ultimately pass this guy we could see that, that I'm just cleaning this up for folks here. We can see that these three instances are all dealing with types and construction of concrete types. Okay, type level considerations. Okay, these three that we just talked about: type signatures, class declarations, and instances of type classes. Okay, these are all statically resolved at compile time. Okay, they are static. They are defined once, and they are used to resolve some of the properties of your types when in use at compile time. Okay, that's what that means. Data constructors are dealing with values. Okay, so those definitions that we talked about, whether we're talking about null array constructors like false or true, or if we're talking about something like our empty list, or even the construction of the list, all right? What we're talking about is these are constructed during runtime, and when constructed, they are a value of that type, okay? And the book in Learning on Haskell and a lot of these Haskell literatures are very explicit about this, which I thought was very nice, because the more precise you are, the more understanding it becomes that the type system really is an opportunity for you to effectively write a correctness proof against your system design. All right. So by understanding what is a value of a type and what is a type, and it's you can understand what properties are occurring at what point they would occur. So you can understand when something is a type error, usually that means it's some property that has been invalidated. Okay. Whereas when you're talking about a value error, that is possibly some sort of runtime issue that during the course of program execution, some case may have arose that was not accounted for inside your system. Okay, so you can look at what point some things can be addressed and see how you can move some of those runtime concerns into the compile time. All right. The only reason why this really threw me off for quite a while until I read this this chapter. The only reason why the term constructor is used is because of constructor has a distinct and precise definition, and it means that you are creating or building a particular thing. All right. In this case of type constructors, we are building a type, and in the case of data constructors, we are building a value. Are there questions about this?
No, I'm good. Thank you.
Cool. The other thing that I found very interesting about this particular thing is at the same time that constructor is being used to talk about creation, they also make a distinction about constants and constructed values. Okay, anything that takes no arguments, so those quote unquote null array constructors, all right, that we saw earlier, like false and true, all right. Or true. These guys are considered constants, type constants inside Haskell. And this makes sense for folks who really, just think about it. It's not a far-fetched idea that basically, although these are concrete types themselves and concrete instances of the type bool, since they're not taking any arguments, they're not parametrically instantiated. So they can be stored and optimized in a fixed way. All right, and as a result, bool, all right. False and true are type are data constants. Sorry, my apologies. These are considered to be data constants, okay? Constant values, okay? Now, the advantages of this fixed type notion, okay, and with these null array constructors is that basically at compile time we can actually make certain optimizations when we realize that they are fixed type and hold and their data is represented a specific way. Bool itself, all right, null array type constructors, all right. So that is taking in no arguments, all right. These are considered type constants, okay. So my confusion there, and you can see that the confusion between type data constants and constant values and type constants is a small subtle difference that you could often confuse them. But there's a reason why it is considered a type constant. What that means is at the type level. So whether you're talking about in a signature or in a type class or in an instance of a type class, you don't need any additional information to construct that concrete type. Okay, which means at compile time, you have all the information you need to do to make a fixed representation of that type, and you can move forward with generating the implementations of all your subsequent type classes that that is implemented for this particular type. Okay. And again, the reason why you would do that is related to the reason why you would want to is related to dealing with, like, say type checking and making sure that at that level those concrete types are already available, and more importantly, the type class instances are also correctly constructed. Again, the type classes don't necessarily need to be implemented, but that's one place where once concrete type is generated, those also tend to be, they tend to fall through if you define a type class implementation for those. Or you used deriving, for example, to actually generate those particular type class implementations. At this point, though, true and false, all right, and null array constructors, all right, those constant values are already established, all right, so they don't necessarily need to be deconstructed and reconstructed at that time. The type checker can actually go and leverage them directly. When we talk about parametric types, though, the use case for this is obviously flexibility, right? You want, just like generics in other languages, you want some ability to take commonality between a family of types, that's what ultimately containers are. They're a family of types. And you want to be able to create a generic kind of contract for that family, allowing different types of data, amounts of data to be stored for that particular family. So in the case of list of A means that you can, if you generate a list of int, it'll know how to represent a list of int accordingly. But in order for that parametricity to be available, you need to pass into your type constructor an argument, like we did earlier, right? And what that means is, and this becomes very, very important later when we talk about kinds, the type constructor must be applied to a type variable in order to become a concrete type or variable, all right? This application is nothing more than an extension of the normal function application we've talked about before, as I understand it. But it's important to know how that this is the case. So when you are defining a template a parametric type in Haskell, specifically for using the data construction, we are we are dealing with something that requires a concrete instance in order for it to actually be satisfied and constructed accordingly. All right, and we've seen this before with two examples that we wrote in previous episodes. I think we've done this one already, the trivial example. This is from the book in chapter 11, right? And we covered this kind of example. You know that on the left-hand side, trivial is going to be a constant type. So it's a type constant. It will act like a constant value when you compile any function that requires trivial. And because it takes no arguments and is a nullary type constructor, that means at the compile time, the concrete representation of the trivial type can easily be created using fixed storage, right? The same thing with the data constructor that we see here. It's a constant value, both in in the in the term level as well, and again at compile time we can use fixed storage to go and represent this particular type. Then we have something like, say, let's say that we have, and we can certainly have multiple. A type constructor can certainly have multiple type variables assigned to them, but we're not going to be discussing that for today. For the purpose of discussion, though, we're just going to be talking about unary types. So we're focusing on unary types, okay? And let's take another example of this. Like, let's say that you had something like, say, some type A, some type constructor, okay, and you're defining it on something. What you're ultimately doing is creating a parametric type here, and when you use, say, some value here that takes in that A, what you're ultimately saying is we're going to use that A and create a concrete instance of the type, okay? Now, there are cases where, for example, that you may end up having, say, something like this, another type that takes an A equals, some sort of another value, all right? This can also occur too, and what that does is there's a phrase here that I like us to discuss a little bit, which is the phantom value, all right? So some type arguments to type constructors may not have value level, may not be used at the value level, right, to construct some value, okay? Some might be, and this notion of a type constructor that takes in an argument that doesn't have a value level construction, that's called a phantom type, a phantom type variable that's been passed in. I don't necessarily know if it means that it's ignored. I think I'm sure that it's not necessarily ignored, but it is something to be aware of, and we're going to be diving into phantom types in just a second. But we've talked about this notion of parametric types and this again this difference that or important requirement that if you have a parametric type, you need to pass in a type variable in order for it to be realized and have a concrete type. In the case of list, you need to pass in something for it to recognize that it needs to represent a list of characters or a list of integers or whatever concrete type you were passing in. All right, that's a discussion that you need to provide. That's information that you need to provide to the Haskell compiler or GHC in order for it to recognize and create this. But when you're talking about at that level, this notion of application, you want to be able to inspect or get some information from GHC about what you're dealing with. Because again, when we talked about types, we showed that you might have nullary types, you might have parametric types, okay? In order to deal with this, to recognize whether or not something is a concrete type or a type that needs to be applied to something, you can leverage something called a kind signature to determine whether or not the type has been applied and created into a concrete type, or it's a type that needs information in order to be constructed again. Kinds, the way the Haskell book describes it, I'm pretty sure that Learn New Haskell does something similar. It kind of determines, in fact, I have to check. I'm not sure if Learn New Haskell covers kinds, at least not at the introductory level as this book does. I might be thinking real-world Haskell for a minute, but there's a couple of Haskell books that I'm kind of covering and thinking about. Kinds are essentially nothing more than type-level information that lets you know whether or not a type has been realized and is a concrete type, or a type needs to be applied to some other type variable in order to be constructed, right? And I just briefly mentioned that earlier. To actually look into this, we need to first understand what Haskell represents types has, well, concrete types has versus types that need to apply, right? In GHC, the type of a concrete type is star. Well, the kind of a concrete type is star, okay? And you could actually see it right here when we define type bool star, right? You can also actually, in the REPL, ask or query it by providing :kind, all right? Or you could also do k :k for shorthand and provide a type information. I'll give you the same information that's in the type signature, right? Info also gives you this information, but you don't necessarily need to know info if you don't require to query about, if you're not querying about what type classes a particular type implements, okay? If you're just asking if it's a concrete type or not, you could just certainly use kind to actually get that, okay? If we use kind on, say, the empty list, okay, which is a data constructor, we'll see that kind on the empty list will actually give us this function, okay? It looks like a function. It is actually a function for many respects. The thing that it's unique about it is the star has the input and the star has the output. What the star represents, like I said earlier, is the concrete type variable, okay? What this is saying is, in order for a list to be realized, it is a type function that requires a type variable, and it will return a concrete variable of that type, okay? So it needs a concrete type variable, and it'll return a concrete type. All right, that is fully realized, okay? And realization is nothing more than applying the type signature to a particular concrete type to make a concrete type, okay? That's what type realization is, nothing more. Take an example, has function definitions, all right? Like f. And, this is kind of an interesting example that I saw in the book. And that is, if we define an f as being just false, right? If we go in and ask for what that type is, we'll know that it's going to be of type bool, right? But if we create a predicate of f and say, okay, f is going to be, greater than some value, If we go and define our query, the type of that, we notice that we end up getting this function signature, okay? And notice specifically that we've abstracted out the fact that we're dealing with an integer, all right, to some numeric value. So it doesn't care if it's an integer. It could be a bool, a real or numeric or numeral or whatever. Anything that implements, the numeric type interface, because obviously that implements, the type signature that could match the comparison of 3, right, with. And more importantly, it implements the greater than operator as specified by the ordinal type class that we covered in past episodes. But the important thing to recognize is the lack of a function arrow when you ask for the type in the case of the constant function of not true versus the actual function signature that's available there that we provided, okay? The kind signature is much of the same way, all right? The kind signature, again, is a type constructor. It is not a data constructor, okay? Because you are dealing with compile time considerations. You're not dealing with runtime considerations when you're dealing with kinds, okay? We'll be dealing with more about kinds as we go along. The main thing to take away from kinds is that they are type constructors. They tell you whether or not a type is a concrete type or not. That notation of whether or not it's a concrete type or not is determined whether or not it is written with a star, which represents a concrete type, or is returned as a mapping that goes from one concrete type to another concrete type, which ultimately means it's defining a compile time type level function that takes in a concrete type and returns a concrete type, okay? By the way, just as a side note, if folks are looking at this and are wondering, well, can this be applied, this theory or this foundation be applied to anything related to generic and parametric type, there's a reason why I'm mentioning those generics from other languages, because for a certain amount of precision, the systems that implements generics and generic types end up leveraging some of the same mechanisms in terms of implementing type realization. It's just this is more explicit in how it allows you to introspect through the types that are provided at the type level versus some of those other languages. Are there any questions so far? I know I've kind of spouted out quite a bit of terminology to folks. Just give me a moment to take a break and a little breather, and we'll continue. Okay. All right. So,
I just want to be clear. For the output for :K on list, it says list : star, arrow, star. So the star just means some concrete type, right?
Yes, it's some concrete type. It is not any specific type. It's just something that has a fixed storage for Haskell. So Haskell knows how to store it at compile time. All right, that's what that means.
Okay.
So we talked about type constructors and type constants. The same kind of notion for type constructors and type constants goes double down for kind of data constructors and constant values, right? Constant values, as you know, are basically nullary constructors that take in no arguments, because obviously they stand and they represent for themselves. They don't need any additional information. This is one of the reasons why, actually, for a sum type, it ends up being what's the word I'm looking for? It ends up being kind of like an enumeration or enumerated type that you would probably see from other languages, right? And you could solely use it in that context. It's just be careful to leverage that analysis, because technically, even though it can act like an enumeration, it does not, as far as I know, unless it implements the enum type class, all right, which usually behind the scenes implements certain kind of orderings. So like if you go and recall enum, oh sorry, why do I keep on doing type? What I mean is info. If you recall in our discussion on enum, it has a fairly lengthy type class interface that needs to be implemented. It ultimately implements, kind of this constraint that's necessary for you to actually leverage. And why I'm bringing that up is although these sum types, especially with nullary constructors and data constructors and constant values, can act like enumerated types, there's nothing actually mapped to them. They're not integral types. Okay, so be careful when you're using enumeration to enumerate between a set, because we're using that term enumeration and enumerating across different data constructors to literally mean going through each data constructor that's in a sum type and checking to see if it's one of those types. What we don't mean is that we can convert one of these constant values into some sort of integer like you would normally see with enumerated data types, like say with enum classes in say C++ or even Java, which early on, if you recall, enumerated types before enum classes were introduced in both languages, they were essentially mapped to integers directly, all right? So they were one-to-one in terms of comparisons. That is not what this is, right? This is specifically just a constant value that represents something at runtime using some sort of fixed storage, okay? That's all that it is, okay? And when you use those particular cases, behind the scenes, the Haskell machine really would leverage this this set, if you will, of different types to recognize that ultimately these are all members of this higher level type. In this case, if we're talking about true or false, we're talking about bool, right? I know that it's a subtle difference, but it's an important difference to recognize, okay? And we've seen actually earlier this when we talked about the enum type class in previous discussions. So I just would refer you to go back and talk about enumerated these enum types earlier, just so that you are aware of it. For folks who are wondering, well, if and I guess it's useful to recognize this. I don't believe, unless you implement this enum for that enum type, okay, that you will get essentially a proper enumeration in Haskell. All right. So you have a sum type. You need to then implement an instance of enum, and then it will become an enumerated type inside Haskell. All right. So we can see here enum is actually set to bool. So bool is a proper enumerated type because we now have an enum from then, and we can actually certainly go to from to as well, and we can leverage all these implementations for that type. And I encourage you to kind of play around with it in your REPLs. All right. The more interesting question when it comes to constant values is the type constructor that we wrote earlier on line 40. Okay, for another type. Okay, we see this type constructor, and we see that the type constructor is a parametric polymorphic type. All right, it requires a type variable as an argument. Okay. And it is defined with one data constructor, all right? and the one data constructor, another value, does not actually take the type variable and use it to create its value, okay? What that means is the type variable, the phantom variable, as I mentioned earlier, it has no witness as to its construction. So this is something that the book mentions that I think is important. This has no witness. What does that mean? I looked into this later on. This is discussed later in the chapter, but when you talk about when you talk about this actually becomes important, not later on here, but it's important that it's there because, and just to kind of skip ahead a little bit to mention this, and just kind of like whet your appetite about this. This has no witness construction is necessary when you're dealing with some of the higher level data type classes, particularly when you start leveraging, say, things like functors or applicatives. Okay, this phantom has no witness construction becomes very, very important in the involvement in the definition of those particular things. Okay, obviously you don't have to be a definition, a type constructor that has a phantom type. All right, we've seen that earlier with unary type construction, but it is important to know that this is a possibility. You could define a type this way. All right. 1 second. I think I still have something here. Yeah. Gotta specify. All right. Just leverage something here. Okay. And if we end up creating, let's say t of some value 5, we can end up seeing that behind the scenes it converts into some type, okay, that takes in a numeric type class. And this is where type realization comes in. All these that we've talked about so far have lone data constructors, but the reason why they have lone data constructors is because of the fact that they are, they're just simple types, okay? One other point that I'm going to kind of briefly mention here, although I discourage this, but it's okay if you have some real reason to do this. You don't necessarily. I mentioned before that type variables are normally in lowercase. Okay. So far, we've seen type variables with single letters. Okay, but that doesn't necessarily mean you need to use single letters. You could certainly change this to being something like this, where we specify some name for it, okay? But the one thing to note is it doesn't matter, because at the end of the day, type names do not they're only necessary for type construction of concrete types, okay? You can also obviously, define your type signature is associated with the types that you're constructing. So, for example, in your buffer, you could go and do, say, let's say type A equals, you know, another value, which is another type, and say that it's an integer or something like this. Would this work? Yes, it will work, right? You can also define, another, type with a signature like we had before, like some type con int, and we can provide type B with some value con 5, and we'll see when we load it and we look at the type signature of type B, it's going to end up giving what we provided earlier, all right? And this keeps going on and on. You can certainly leverage all of these kinds of like stuff. You can also obviously have a sum type with multiple data constructors that take in that type variable. So, we could create a type called person, let's call it ba, of some A, and this can be, considered either a foo of A, or a baz of A, bar of A, or a baz of A. Okay, and what's interesting about this is, and again, I'm not changing any of the notation here. Like you can, this is kind of like the indentation that they're expecting, and it's kind of working. And if you want to go and say that you want to implement certain type classes, like I mentioned, and we've kind of covered this before, you could just specify those that you want to mention here. And as soon as you compile them, as you see here, we can actually, leverage that. Okay. Again, though, if you go and look into the kind of this guy, it's going to end up being a type that requires some sort of information. All right. If you end up providing, let's say, one of its, let's say it's one of the data constructors, and we ask for its kind. Sorry, not kind. You'd have to get the concrete value of it, you need to actually go and type in foo, and you'll end up getting this. You will end up getting the type signature of the actual data constructors. This is something that's important to that we need to recognize. Types have kinds associated with them, right? Type constructors have kinds associated with them as to whether or not they need to require a type variable in order to realize themselves and become a concrete type. But data, the definitions of the value constructor, the data constructors, in order for them to become concrete values, if they need a parameter, then they ultimately become function signatures. Okay, so what is that function signature? That, as you see here, it needs some sort of parameter, a type variable A, in order to construct a new instance of the type ba of A, as we defined it earlier as being a sum type. So what does that mean if we go and provide foo5? If we do this, you'll see immediately everything has been realized. We've made the requirement by the type checker that this has to be some sort of numeric value, and then it will still return, ba of A. The types classes, if there's a type class instance that's already there, it's going to become part of the signature when you go and construct that type at the value level. Okay, That is something that you cannot avoid unless you don't implement. I mean, the only way to avoid that is if you don't implement the particular type class. But if you do that, if you register any type class instance for a particular type, all this checking, all the constraints, that's added to you to an extent automatically. Not to say you shouldn't provide that in function signatures. I'm just saying that when you're creating these concrete instantiations and trying to play around with the REPL, you'll see immediately that this type class constraint is added, like we've seen in the past. So I briefly mentioned before that the differences between types and data, right? And the important this distinction in the compilation phase of whether or not we are constructing a type or we are dealing with a constant value. Again, types are static when we're dealing with Haskell types, and their resolution are done at a compile time. It's the only way to actually go and make sure that things are lined up and actually go do proper type checking. Okay, so they are known before runtime through explicit declaration, either through explicit declaration or through some sort of type inference mechanism, and then they are used. Okay, the information that's generated from them, they're not persisted for you to introspect at runtime. Okay, rather, what we're dealing when we're dealing with runtime is instances of those types through their data, through their values. Okay, that important distinction is subtle when you use other languages, because normally when you're talking about statically typed languages, they don't have this kind of like definition. But it is kind of the same thing to think about. Your types and their type information through either declaration of the types or type inferencing, you are going to be dealing with those considerations at compile time. And when you're dealing with the actual values of that information, you are going to be dealing with those things at runtime. So how does this affect our program design? Well, remember, compile time checking is nothing more than looking at the type construction and verifying the type signatures at the time that you are compiling and making sure that those types all line up. Okay, that's what compile time type checking is. Okay, and that's all it can do. Right, even in GHCI, if you're running in interactive mode in the REPL, ultimately what your type is being, and your type signatures and your functions and their applications, they are ultimately going to be checked first before they are executed and before they are compiled and executed, inside the REPL, okay? At that point, you're dealing with values, and when you're dealing with values, you're dealing with data flow with respect to the type signature flow that you provided earlier at compile time. All right. There's a couple of nuances here that I just want to briefly mention regarding data constructors and type constructors that you may have noticed from our examples, but I'm just going to mention them ahead. This is kind of like Haskell Haskell-specific considerations when you're constructing these things. The one thing that is important to note is you might be so inclined to try and create some nonsense type, called data.bar a equals bar a, all right, where we have the data and the type constructor written the same here. you're going to end up getting an error because data constructors and type constructors need to be capitalized. They need to have a capital letter as the first letter of their names. Okay, this is just a important thing to be aware of. Okay, so let's if we call this rab, actually let's do that and do this. This might be a better way of doing it. You can see that there's not a data constructor. We create this, and now it's not a type constructor, and we need to now have a type constructor and data constructor. This is the other thing to recognize. You could have type constructors and data constructors with the same name, all right? This is the other thing that kind of screws with some people when they're looking at it. There are some cases where you want it to be the same name, just because it might be representing a more restrictive type. An example of this is if you're dealing with money, all right? You want to kind of have a concrete representation of the money. Say, you use, data money equals money int, okay? Deriving EQ show, all right? Let's say that in not even money, we call it dollars, all right? Just to make it simple, all right? Obviously, there are different types of currency, but for the time being, let's use dollars, okay? Here, we've created a data constructor, a type constructor that has, a capitalized dollars on the left-hand side, and we're using the same name to restrict it to being of type integer, okay? So the restriction of the type and the construction of the type is actually done on the right-hand side in this case, but not the left-hand side. This is an example of a concrete type still, and we could see that if we go and let's look at the kind of dollars. Right? That's another kind of thing that would definitely kind of screw with some people. The one thing to note about this concrete construction is if the type that you provide in the data value constructor, okay, does not exist or is not in scope, you'd be unable to generate new instances of that type, okay? And that's because the value constructor, all right, for dollars in this example, it depends on two things, not just the data type definition, okay? Not just what the type constructor says. It requires the secondary type to be available at the time that it gets constructed. So that's why if you have a type that's from some third-party library that doesn't necessarily get into scope at a certain point, you would end up getting some type errors because of the lack of the availability there. So make sure that you appropriately import your modules accordingly to actually use those types.
I'm a little confused here.
Sure.
How at the replicant would you use dollars, right? The dollars is dollars int deriving even show. But can I say $5? Foo equals $5 or something? How do I do this?
Yeah, so foo equals $5. Okay. Type foo is now dollars. Okay.
Okay.
So the type.
So then, just that foo is $5 or $5. Foo equals 5.
Foo equals $5.
When we type in foo, it's going to say $5.
Yeah, that's right.
Okay.
Foo is only going to be equal to $5. We haven't actually provided anything here that will convert it to some other type, right? Because ultimately you have to do a type conversion to convert it to use it something, or you provide some operations on top of the type in order for you to leverage the underlying value of that type, the underlying value behind the data. That's it, the data constructor.
Okay, so for instance, we couldn't say foo plus 5, foo plus 3.
Yes, this will get screwed up naturally because the types don't match, right? Because you need to convert. You need to essentially implement the numeric interface, get the value out of the data constructor, and then you can then leverage everything else.
Okay, thank you.
The type information is almost as if, in a sense, the type information. And I think I started to slowly realize this in Haskell serves two purposes. One is it's adding semantics to your program. All right. It's forcing you to essentially define your domain in such a way, and the operations in such a way, you're no longer thinking about the primitive types. So in this case, you're not thinking about dollars as an integer like you normally do in mainstream programming languages. You're literally thinking of this as an object that internally represents a certain, has a representation that's an integer. All right. I don't want to use the term containers here, just because I know some folks might be leaning towards that definition, but there is a subtle difference between what we call a container and a normal data type. All right. I'm not saying that all data types aren't containers, because there are container data types like list or map or dictionary or whatever, right? I'm saying that to explicitly talk about every type as being a type of container, you are missing some of the information associated with what that means. All right. Subtle difference, but it's an important distinction to be aware of. Containers and types are slightly different. So that's kind of where I'd like us to stop at for now, because there's a lot of information that needs to be kind of digested here, related to the terminological foundations that are here, right? And I know that for some folks that this is going to be a little pedantic in many situations, right? But again, the reason why you want to understand this terminological foundation is because at the end of the day, when you're starting to design your systems and you want to figure out certain patterns that are associated with using Haskell, you're going to end up more than likely end up leaning towards the literature, and you want to be able to, at that point, determine what is useful or not useful. And the best way to do that is to know these terms so you can read and understand some of that literature to make your best judgment. So that's it for today. Next week, we're going to finish off our talk about algebraic data types to include things like arities and multi data constructors and type constructors that take up that are multi-arity, that are n-arity type constructors and n-arity data constructors, and then we'll talk about a little bit more of the specific parts of what it means for things are to be algebraic, which we've been kind of alluding to. It's related to kind of the type variables, but also it is related to the argument structures that define the type. So we've already talked to them about. We've talked about some types and product types, and in the past we've talked about this notion of cardinality, especially when we talked about pairs and tuples. So we're going to dive a little bit more in deeper discussion to that, but I'm just going to hold out on that. Just a reminder for folks, next week Thursday, 7:30 to 9:30. Actually, I'm probably going to make it 7:40 just to give people enough time to chime in. Folks who are looking forward to a meetup announcement, I'm setting up the meetup announcement so that you guys can actually look it up. Those of you who are not part of Atlanta Functional Programming, I encourage you to go to meetup.com and join us. A lot of Haskell study groups are available online. We actually do them only online right now. And in the near future, we're going to continue to doing them, even if we go back to kind of normal meetups happening in person. A final note: Atlanta Functional Programming is looking for speakers. Those of you who are interested in giving a talk, please ping me. I'm Bugram on Tech404, and I'm also available as Bugram on the Lisp Discord server. I hang out in both of those places. And I'm also available on the Functional Programming Slack channel as Bugram, both hanging out in both the Haskell and Lisp chat rooms. Just mention me or DM me directly. Say, hey, I have a topic, and I will set you up into the schedule. So until next time, I hope you all have a nice Thursday evening, and I'll see you later.